Hello and welcome. Welcome to the Gutermann Leak Detection 101 webinar. We're happy you can join us today. I'm going to be your host, Eric Galosi. I'm the commercial director for Gutermann USA. And as usual, assisting me on today's webinar is my colleague, Max Ward. Say hello, Max.
Hello, everyone.
Thanks for joining us. Max will be behind the scenes, making sure this webinar runs smoothly. He'll be handling your chat questions. At the end of our presentation, we will try to answer those questions, as many as we can. I see we still have some folks joining us, so we'll give a minute here for everyone to join and get themselves comfortable. It's good to see so many people participating with us today. We have a fantastic webinar planned for you today. We're going to talk about the basics of leak detection. We call this Leak Detection 101, but I think by the time we're done with our 45 minutes here, you will have a master's level degree of knowledge with this leak detection theory and practice. The next 45 minutes will be chock full of valuable information, how the equipment works, how to apply that knowledge, with the ultimate goal of reducing your non-revenue water, finding your leaks. And with that, let's get started. Okay, Leak Detection 101. Let's get started with localize, locate, and pinpoint. We call this the three-step strategy for active leak detection. Localize means that you're going to narrow down your area into DMAs, neighborhoods, manageable areas within your overall system where you think you have water loss. If you have master meters at DMAs or into subdivisions, this would be that layer of localization to get you started and focusing on where you want to do your leak detection. Your locate is going to be the location, the activity that you undertake to locate the leak, locate the position of the leak, using our noise loggers or our noise correlators. And then finally, once that leak has been located, we want to pinpoint it, using your ground mic to fine-tune the exact location of the leak, to allow you to dig as small and as accurate of a hole as you possibly can. Using the ground miking equipment will allow you to do that. And in addition, following these three steps, you are then assuring yourself that you've taken all the steps that you can to ensure that you're locating and pinpointing down to the very precise point on the street of where that leak exists. The theory of leak detection begins with sources of pipe noise. What we're doing when we're searching for leaks is we are really looking for sound. That leak on a pipe creates a sound. And in fact, not only does the leak create a sound, but there are sounds all around us. And those sounds can come from a variety of sources. Consumption, water flowing through a meter, pressure reducing valves, proximity of pipes to other pipes, changes in your pipe diameter, water pumps, electrical transformers, air conditioning units. The list goes on that can create a sound that would be detectable with our leak detection equipment. A leak on a length of pipe creates a noise, creates a substantial noise, as a matter of fact. You have water in a high pressure environment inside the pipe, escaping through a small hole or a small crack in the pipe. And that water undergoes a pressure differential, a pressure drop from high pressure inside the pipe to low pressure outside the pipe. And it's that pressure differential, that pressure drop that water experiences as it goes through the break that creates a vibration, a mechanical vibration. That vibration is sound. And it's that vibration that travels through the wall of the pipe and travels down through the pipe network. That vibration, that sound, is what the sensors, your leak correlators, are picking up when they are doing their leak surveying. The material of pipe impacts the quality of the sound. As you can see, steel, ductile iron, copper, cast iron, they allow the propagation of sound to travel much better than your softer material pipes, such as lead, PVC, HDPE. Those more brittle steel and ductile iron and cast iron pipes allow that sound to travel much more freely and travel a greater distance through the pipe network. Also, too, the higher the pressure, the better sound you're going to, that the leak is going to create. And as you can see, our chart on the right-hand side, we have an idea. We can have a general idea of the type of sound that is being created based upon the material of pipe. The frequency of sound is measured in hertz, and each material of pipe transmits sound in a particular, almost predictable hertz range. So you can see the frequency ranges of the various materials of pipe. We can use these hertz ranges to fine-tune our filtering to listen to leaks on a variety of materials, including lead, PVC, and polyethylene pipe. The backfill that the pipe is resting in also plays a role in how well that sound is being propagated down the pipe. As you can see, a porous backfill allows that water, as it's escaping the pipe, to escape into a low pressure environment. Remember, the higher the pressure differential from high pressure inside the pipe to low pressure outside the pipe creates a better sound. The higher the pressure drop that water experiences, the better the sound is going to be created. In instances where you have a very non-porous, a clay or very thick backfill, that escaping water cannot drain away as quickly. And over time, a leak will actually build pressure outside the leak area. You'll get a cavity that creates back pressure. And that reduces the pressure differential between the inside of the pipe and the outside of the pipe. As the water is unable to drain away easily, your pressure differential reduces between the inside and the outside of the pipe. And subsequently, it creates a lesser sound, a more difficult sound to hear. Not much of energy that is created from that leak, and it becomes a little bit more difficult to hear. Also, too, the size of the leak plays a role in how well the sound is propagated down the pipeline. A small pipe rupture creates and maintains that high pressure differential between the inside and the outside of the pipe. Thus, you get your loud and high frequency noise. The larger the leak, the less pressure that is maintained inside the pipe, and therefore your pressure differential drops, and you have little to no noise propagation. Once you get to the point where the pipe splits completely in half and you have a main break, these are very difficult leaks to hear, simply because you have almost a complete pressure loss inside the pipe. And the pressure inside the pipe equals the pressure outside the pipe. And once you get to that point, no sound is created. Now, of course, you're going to find that water main leak in different ways other than hearing it. You will certainly begin to see water up on the bubbling up on the street, and many times that is frustratingly too late. So the conclusion is, you prevent your large breaks by monitoring the leaks when they're small and the system pressure is highest. And thus you're finding, and you're attempting to find those leaks when the listening environment is ideal. If you're doing overnight listening, you can do this by doing your listening overnight, usually at 2 a.m., 3 a.m. in the morning. This is theoretically when your system pressures are your highest, because your service draws, your consumption is lowest at that point. So the basics of correlation theory is leak on a pipe creates a sound wave that travels through the pipe wall. It creates an amplitude and it creates a frequency. It's this frequency or the hum of the pitch of the leak that our sensors are picking up. The data, the sensors are just picking up sound. The data is compared with your software program, your processor, ZoneScan-Net, your 610 processor. That data is compared and analyzed. And what the processor is doing is looking for a similar sound, a peak sound. It is looking for sensor A to be hearing the same thing that sensor B is hearing. And when you have a similar sounding, two sensors hearing the same sound, you get a peak, and what we refer to as good correlation. When two sensors are hearing dissimilar sounds, when there is no common sound on the length of pipe, you get what we call a Manhattan skyline, or the poor correlation. The two sensors, A and B, just aren't able to come up with an agreeable common sound from the pipe, and therefore you have poor correlation. We can take this similarity of sound, and in addition to being able to time the speed of sound down the length of pipe, and we do that by knowing the sound velocity, all pipe, based upon its material and diameter, has a predictable rate of speed that sound will travel down. We know what those are. And if we know that rate of speed, and we know the total distance between our two sensors, the D, and we know our speed of sound on the pipe, the V, and we also know the time delay, how much sooner the leak sound is reaching one sensor, the closer sensor, to the farther sensor. With those three variables, distance between sensors, speed of sound on the length of pipe based on the pipe material and diameter, and the time delay, how much quicker sound is reaching the closer sensor as opposed to the farther sensor, it becomes a simple mathematical equation to figure out where the source, the distance of the source of the leak is in relation to A and B. And here is the equation on the screen right in front of you. You can actually put in the numbers, do the math, and you will come up with this, with the mathematical pinpointing location of the source of the sound, the exact source of the sound on the length of pipe. So to continue with our correlation theory, the objective, the goal of the sensors is to pick up the sound, is to hear the leak sound. So sensor placement becomes key and necessary for you to capture that sound. What we want to try to do is position the leak in the middle third of the distance between the two sensors. When you have the leak too close to one sensor or the other sensor, the accuracy can tend to diminish because the sound emanating from the leak needs to travel such a far distance from the leak to the far sensor as opposed to such a close distance to the close sensor. You introduce a lot of opportunity for error. If you have repair clamps on your pipe, if there's corrosion on the pipe, if there are other instances that may affect the speed of the sound traveling down the pipe, that is going to affect the mathematical equation. So to eliminate the possibility of inaccuracies, trying to position the leak in the middle third of the two sensors will go very far in eliminating those unknown variables and inaccuracies that you may experience because of repair clamps or corrosion, or the fact that you may not even truly know the true size and diameter of the pipe. Placement of the sensors also, in addition to positioning the leak in the middle third of the sensors, you need to position your sensors in a way that the leak is in between the two sensors. You can see in our first setup here, we have a typical T. We have the leak up on the T, as you can see here, but our sensors are along the main. These sensors are going to correlate, and they're only going to be able to tell us that the leak is emanating from this point, this center point on the pipe, or this middle point on the pipe. As you can see in this example, that's not necessarily where the leak is, but that is the common point on the length of pipe between the two sensors that they are reporting back a common sound. The processor is sensing that, is reading that sound. It is a common sound. You're getting the peak. And the mathematical equation puts the source of the leak right here on the pipe. However, as a leak detector, a smart leak detector would do, recognize that you're on a T or even an intersection and not quite be happy yet with the accuracy of that leak. In the second setup, we actually remove one of the loggers from its current position and move it down the pipe. Reposition it, run a new correlation, and now we've positioned the leak in between the two sensors. This length of pipe is no longer a straight length of pipe, but an L-shaped pipe. That's quite all right. But we've positioned the leak in between the two sensors. Now the equation and the computation of the leak is going to bring the leak back to, or position it in the exact spot where the leak is correlating. We could actually do a third setup here and move this green logger over to where the red logger was in the first setup and run a correct side L correlation, so to speak. And we would come back with the exact same result of the leak being on the T. So interpreting your results of your leak detection using your processor, whether it's the 610 or the 620L or the cross-correlation graph in ZoneScan Net, You can see here where you are looking for a sharp peak in between our sensors. For those of you who use ZoneScanNet, this cross-correlation graph should be quite familiar. The blue peak indicating the intensity of the leak emanating from the length of pipe. The x-axis along the bottom is the length of pipe. Your two vertical black lines, you have one at 0 feet here and the other one past 500 feet here. Those represent the positions of your two loggers. And then the peak in between those two logger positions on the pipe indicate the source of the common sound emanating from the pipe. And as you can see here, we've got great correlation, 100%, meaning that ZoneScanNet in this case is hearing the exact same thing from logger 484 as it is hearing from 556. Using the equation, knowing that the speed of sound on the length and material of pipe that we've inputted, we can now come up with our mathematical equation that the leak is 116.1 feet from logger A, sensor A, or logger 484. This gives you a great correlation because that leak is in the middle of the two loggers. Our example down below shows a leak that is drifting off and over and very close to the far right sensor. In this case, you have a leak. You're getting a great correlation, but your leak peak is not quite as wide, not quite as narrow. It's a little bit more pyramidal. And in this case here, you can certainly do yourself a great deal of improvement by doing another correlation where that leak peak is positioned between two loggers. So in this case here, you might want to do another correlation and move a logger a little bit farther down the line, knowing that your leak is somewhere close to where your first logger was positioned. By putting a logger farther down the line, running another correlation, you've now positioned your leak in the middle third of two loggers, and your accuracy is going to increase dramatically. And here's an example if you're using the 610. This graph should look familiar to you. In the first, at the top graph here, we have a leak that is very close to sensor A. And then in our second example here, we have a leak that's very close to sensor B. And then our third and correct correlation, we've positioned our sensors to create the leak more in between A and B in that middle third, and our leak peak improves dramatically. Of course, you always want to be aware of exact center correlations. This indicates that one of the sensors may be turned off or not listening properly. And that will be cause for concern. And of course, when you don't have a leak, using the 610 correlator graph screen, you have that Manhattan skyline that we call. No common sounds being generated on the length of pipe between your A and B sensors. And therefore you get a very low quality or no correlation at all. You can see here at the top example, poor leak noise and poor correlation. A lot of noise, a lot of dissimilar sounds emanating from the pipe. Nothing certainly that the two sensors are able to focus on. The next example is a typical PVC leak. You certainly can find leaks on PVC. Your sensors tend to need to be usually closer together in order to capture that sound, as the PVC absorbs the sound and the sound wave doesn't travel quite as well down the pipe. But you might have a peak that's not quite as crisp and clean as you would on a piece of ductile iron. You also too can find two leaks. If you have two peaks, two distinct peaks in between your A and B sensor, that might be indicative of two leaks occurring on the length of pipe. Okay, so We now know the basics, the theory, the math of how correlation is done. We've got sensors collecting sound. The sound is compared for a match. Pipe data is entered to allow us to figure the speed of sound on a length of pipe depending upon the pipe's material and diameter. We know the equation. Let's go out and find a leak. There are a couple steps that you need to take to undertake successful and efficient leak detection. First, you want to set up your correlation area. We're going to go out in the field. We have a potential leak on a street. We want to go out to the street and locate all the possible access points to place our sensors or loggers down to capture the leak. And there is a general ranking that we do. The main line valve is the best. A hydrant valve is good. And then if you don't have any of those access, putting a logger on a service or a meter or a curb stop, and you may even have to put it on a valve key down on a curb stop. But what you're trying to do is get the sensor as close to the source of the leak as possible. Now, the Gutermann sensors and correlate the sensors and loggers, they're easy to use. They're flexible as far as small and compact. So they can go in some tight areas, as you can see, down in valves or meter boxes. Once you've established your access points, you now need to measure the distance, accurately measure the distance between your two sensors. And remember, now that we know that we're using a mathematical equation to pinpoint the exact location of the leak, accurate measuring is a must. If you're using a measuring wheel, take your time as you walk between one sensor and the other sensor. Walking fast can tend to make that wheel wobble. If you hit little grains of rock or debris, it'll jump, and it'll knock off your accuracy. So take the time, do your leisurely stroll between your two sensors to get an accurate measurement. And then finally, deploy those sensors on the valves. And finally, and just as importantly, make sure that you're making good metal-to-metal contact between the sensor and the valve nut. There are magnets on the bottom of these sensors. If you can establish magnetic connection, all the better. Even if there's a little bit of dirt and you're not feeling the good metal-to-metal connection or magnetic connection, please take the time to clean out the valve to make that good connection. I have a pole that has a hook on it that I use to lower my loggers down into the valve chambers. At the other end of the pole, I have a little wire brush for rotary paint removal that I have attached to that end of the pole, that I can flip the pole over, put the wire brush down into the valve, give the valve nut a good brushing with the wire rotary sander. And that ensures that I'm getting a good clean connection. Real easy to do, and it'll improve your results dramatically. Gutermann has a full line of products that correlate, that will pinpoint your leak. The ZoneScan 820 Alpha, 820 in the Alpha, the AquaScan 610, 620 in the trunk main correlator. Our new nb-iot ZoneScan loggers, the Easy Scan, Multi-Scan, and High Scan systems all will correlate and pinpoint your leaks down to that precise point on the street. So now you know that there's what equipment is available out there for you to do leaks. You've got a general understanding of how to do the leaks, the theory behind it, and you're pretty confident that you can go out and do some leak detection. There's a lot of products out on the market. There are a lot of choices for you to consider when doing your leak detection. But I find thinking about your leak detection in two camps is going to go a long way with helping you decide which equipment to use. And those two camps are the reactive approach and the proactive approach. Reactive, meaning, hey, I've got water bubbling up on the 100 block of Elm Street. I need to go out there and shoot the leak right now so we can begin digging. And then proactive, hey, we've got a lot of water loss in our system. I don't know exactly where it's going, but we would like to try to narrow that down and find where those leaks are. So the reactive approach can use the Aquascan 610 or the 620, the Easy Scan, the Multi Scan, and your ground mics, as well as the zone scan loggers. But reactive leak detection is finding a known or suspected leak, going out into the system, placing your Aquascan sensors on valves and hydrants, and capturing your leaks immediately. You can expect to mostly find your valves, your services, and your hydrant leaks with this type of reactive leak detection. Your proactive leak detection, finding those unknown leaks. You're going to do this by systematically canvassing your system, putting zone scan loggers or zone scan nb-iot or high scan sensors in your system over a broad area, and let them listen over a length of time. This is where a permanently installed system really shows its value. The great thing about proactive leak detection is that you are finding the small leaks, leaks that are not causing any concern on a reactive basis, meaning that these are leaks that are not surfacing. There's no customer complaints. There's not a significant a pressure drop in an area in your system. These are leaks that are running in your system right now as we speak. Undetected, might have been running for weeks, months, or years, that just aren't surfacing, but are causing a tremendous amount of resource loss as it continues to leak. So your proactive leak detection is going to address that, and you will begin to lower your unaccounted for water loss rather quickly as you begin this surveying, this system-wide surveying. So now you have a general idea of, okay, what kind of leaks am I searching for? Proactive or reactive? You're ready now to create a leak detection program. Your goals of the leak detection program are going to utilize your equipment that you just put so much attention and resource into securing and purchasing. You want to maximize your crew efficiency. You want your crew to go out there and spend as little the time as possible finding and pinpointing that leak. And you can. You want to find and pinpoint those non-surfacing leaks with the ultimate goal of decreasing your water loss, and then the ultimate goal of increasing your revenue. Knowing this, the return on investment is quite visible for a leak detection program. An effective leak detection program with the right equipment, efficiently run, is going to provide numerous paybacks, not only in the elimination of the loss of your water, but reduction of man hours repairing pipe, the reduction of chemical costs for your treatment of your water, the reduction of your electrical pump costs for pumping of the water, and the reduction of your mainline breaks. Finding the leaks when they're small pinholes will stop that leak from becoming a main break 2, 3, 4 months down the road. So doing proactive surveying of your system is going to go a long way and provide an immediate return on your investment. There are countless case studies out there that show what these savings are. Your authority may have already done some mathematics to figure out, and some budgeting to figure out what your leak detection program is saving you. And there are authorities out there that probably have done the math also of what their water loss is costing them. And there are plenty of resources for you to learn about water loss. In particular, the AWWA provides the free water audit software. And if you go to awwa.org, you can access that water audit software. And it looks something like this, recovering your actual non-revenue water. The statistics are out there. There's plenty of data on water loss throughout North America and throughout the world. In North America here, the bottom line is the average water loss in the system is about 16%. But more shockingly, at least 2/3 of that water loss is easily recoverable. The water loss audit, the AWWA water loss audit, has put together a fantastic graph here. This will help you working from left to right as you fill in all of the variables based upon your numbers. As you continue to work from left to right, eventually you'll get to the lower right-hand corner, the non-revenue water. That will give you your exact water loss, non-revenue water loss figure. And that is the 16% that I just referenced a few seconds ago. So the AWWA has set standards. That graph allows you to create a very accurate picture considering all the other types of water loss. The AWWA water audit creates an accurate picture of your water loss, your unaccounted for water losses. In other words, your leaks. And with that, thank you very much for tuning in to our Leak Detection 101. You are now not only just basic leak detectors, you have a firm grasp and almost a master's level grasp of sound and sound propagation and leak logging. At this point, Max, I think we will take some questions.
All right, Eric. We have one question so far. Joseph asks, how does changing of material from one sensor to the other? I think this means if there are two sensors and there's multiple materials between those two sensors, how does that is that possible, and how does it affect the correlation?
Yes. When you have your sensors on pipe, there is possibility that your pipe will change material in between your sensors, and that does indeed play in the accuracy of your leak location. Your leak detection software, whether it be the ZoneScan Net or your 610 processor, allows you to put in multiple segments of pipe in between your sensors. So you inputting that correct material and diameter as it changes between sensors will allow the software program to recalculate the math to still accurately pinpoint the location of the leak. The greater point is, yes, change in pipe material and diameter in between two sensors isn't going to cause a problem as far as pinpointing the leak. But you, as the operator, the leak detector, you need to provide the software, the processor, with that knowledge in order to accurately pinpoint your leak. So good question. Any other questions, Max?
Yeah. Let's see. There's a question about if the materials are indeed accurate in the GIS data, will ZoneScan automatically account for it? I think this is more of a ZoneScan question, but still.
Yes, if you're sending your data up to ZoneScan.net and your GIS data that's on ZoneScan.net is accurate, and you can trust your GIS person that they put in accurate data, then ZoneScan.net will just use the data that's embedded in that GIS, and you will get your pinpointing. However, it's not a perfect world we live in. Now and then your GIS data might be inaccurate, wrong size, wrong material. In ZoneScan.net, you can actually go into ZoneScan.net and manually change your pipe segment, your GIS pipe segment, to a different material to allow ZoneScan.net to accurately correlate and pinpoint the location of that leak. So even though your GIS data might be wrong, ZoneScan.net allows you to go in and edit that segment of pipe to put in the correct pipe material or pipe diameter. And ZoneScan.net then will automatically correlate that leak and provide you with the new position. At that point, you should go back to your GIS team and say, hey, we've got a mismatch here in the GIS data and what we have out in the field, and allow them to make that change. At which point, then you can resend me the GIS data, and we'll upload your new, more accurate GIS data to ZoneScan.net. Good question. Thank you very much.
Great. Just a quick heads up. So if everyone can see the chat window, if you could go in and enter in your name or email, and I will be the only one who can see it. So that way, if you have a question or would like a link to the video when we upload it tomorrow, we can get that to you as soon as possible. Let's see. So just kind of waiting here.
While Max is waiting there,
go ahead.
This leak detection 101 that we've put together, if you or your authority or your employer, you need to get credit points, we're more than willing to provide you with either a live webinar training, or as Max stated, this will be posted shortly tomorrow. I think this will be posted on YouTube, that you can access this full training. But if you need credit hours, this is a fantastic way to do that. And we're more than happy to, if you reach out to us, we're more than happy to provide you with the resources, whether recorded or live, in order for you to run this webinar again.
Great. Well, it looks like we have only messages coming in with emails. So not many questions left, but
okay. Well, with that,
yeah.
On behalf of myself and Max, thank you, Max, and the rest of the Gutermann family throughout the United States and the world, we thank you very much for tuning in to our Leak Detection 101 webinar. Be safe out there and go find some leaks. Thanks a lot.
Thanks, everyone. I'm going to stay on for a couple more minutes if you still need to send in your email, and then I'll be signing off.